2D kinematics is the movement of objects in the x and y direction, meaning that the object is moving vertically and horizontally at the same time. The three kinematic equations are the following, where VI represents initial velocity, VF represents final velocity, and A represents acceleration. Likewise, T represents time, delta X represents change in position or displacement. Another useful equation to know is the velocity equation, where V represents velocity, D represents displacement, and T represents time. Remember that for each equation, only one dimension can be focused on at any given point. For example, if you are looking at the final vertical velocity, you cannot solve the equation with the initial horizontal velocity. Let's see some 2D kinematics in live action. Here we've got the rare footage of a battle between a pack of wild nerds. Watch closely and observe the movements of these strange, unique, and beautiful creatures. Watch as this majestic bard is preparing for battle by tossing her weapon into the air. Let us figure out what speed she is throwing her weapon with. We know it will take 0.5 seconds for the ball to travel from her hand to the apex, or the highest point reached. Using the equation Vf equals Vi plus At, we can solve for initial velocity Vi, which is the speed at which she is initially throwing the weapon with. We will treat final velocity, Vf, as the speed of which the weapon is at the apex. Since there is no horizontal movement, we will only focus on the vertical movement of the weapon. At the apex, velocity is 0, thus we can substitute 0 meters per second for final velocity. Acceleration will be the force of gravity, 9.8 meters per second squared. Remember that acceleration of gravity is downwards in this case, so when substituting the value for gravity into the equation, make sure to make it negative. Finally, we will plug in 0.5 seconds for the time. All we don't know now is Vi, so we simplify the equation and arrive at the answer. The bard throws her weapon at 4.9 meters per second. The woodland defender prepares her own attack from above. Let's say we know she throws the weapon with a velocity of 1.3 meters per second. Let's figure out the vertical velocity of her weapon just before it reaches her opponent. We will use the equation Vf squared equals Vi squared plus A delta X and focus on the vertical direction. When the weapon first leaves the woodland defender's hand, it but only has horizontal velocity and no vertical velocity. Because we are only focusing on the vertical direction here, Vi equals 0 meters per second. Acceleration is once more gravity, which we know is negative 9.8 meters per second squared, and delta X was given to us as 2 meters. If we solve for Vf squared, we get that Vf equals 4.43 meters per second. Oh ho ho, but what if we want to know how long it takes for the weapon to reach the bard from the woodland defender? We will use the equation delta X equals Vit plus 1/2 At squared, once again focusing on the vertical dimension. We know that velocity is 0, thus causing Vit to be 0. So we are left with delta X equals 1/2 At squared. And delta X is given to us as 2 meters. Acceleration is gravity, 9.8 meters per second squared. Thus, solving the equation, we know T equals 0.64 seconds.
What you say? Oh, that you only meant when.
The bard has been slain, and her comrade grieves her death. But now, fueled with vengeance, watch him slay his enemy. Let us assume that the opposite warrior's face is at the same level of the mage's hand. When he throws his mighty weapon, he throws it at a speed of 3.5 meters per second and at an angle of 23 degrees. But let us figure out how high this weapon goes. We will use the equation Vf squared equals Vi squared plus A delta x, once more focusing on the vertical component. Vi in the vertical direction can be calculated by multiplying the total velocity, 3.5 meters per second, by sine theta of 23 degrees. Make sure your calculator is in degrees for this equation. Vertical velocity in the direction will be treated as the apex. Vertical velocity is 0 at the apex, so we know that final velocity is 0 meters per second. Acceleration is the acceleration from gravity, 9.8 meters per second squared. In solving the equation, we get delta x of 0.3 meters. Now let us figure out the time the weapon is in the air. We will use the equation Vf equals Vi plus At. Vi is once again 3.5 meters per second. Vf in the vertical direction will be treated as the apex, so final velocity is 0 meters per second, and acceleration is once more gravity, 9.8 meters per second squared. So thus, we can solve the equation and get a time of 0.36 seconds. The time it takes for the weapon to travel to its apex from a particular point will be equal to the time it takes for that weapon to travel back down from the apex to that point on the same level as the original point. So we can multiply the time t we calculated by 2 in order to obtain the total time the object was in the air. In the same manner, by the symmetry of motion, the velocity with which the weapon was first thrown is equal to the velocity at which the weapon will land, and if the weapon is thrown and lands on the same level. Now let us figure out how far the weapon has traveled horizontally. We can use the equation Vx equals dx divided by time. Because time in the x direction is the same as time in the y direction, we can use the t-value we obtained in this equation. It is important to note that the horizontal velocity remains constant throughout the path of travel, but the vertical velocity does not, due to it decreasing due to acceleration as the object starts going towards the apex, and increasing as the object travels away from the apex due to the acceleration from gravity. Here we are just focusing on the vertical component, so the velocity in the horizontal direction, Vx, is a constant value. Vx can be obtained by multiplying the total velocity, 3.5 meters per second, by the cosine value of 23 degrees, and the time of t is the value we obtained earlier. When solving the equation, we can get that dx equals 1.34 meters.
What you say? That you only meant well, 'cause you did. What you say?